generally you're not going to be Thanks.
Well, first I'd like to thank CITA for inviting me here. I'm going to be talking today about some new discoveries that we've made through some numerical simulation. Enrico always tells me that you don't really discover terribly much via numerical simulation. The few key exceptions have been the MRI and a few others.
The MRI was discovered analytically, I think that was.
Yeah.
We demonstrated, well, no, I think Balbus.
It was analytic first.
Yeah, Balbus has some analytic arguments, and then Polly did simulations.
So precisely my
but I disagree with them. I think a lot is discovered numerically.
Right. So I wanted to dispel this notion a little bit that we can't discover things numerically. And so in particular, I'm going to be talking about tidal disruptions, and I'm showing here a snapshot from the 3D simulation I did of the return of the matter after the disruption to the supermassive black hole. I'll talk more about this later. It's just a nice, pretty picture to show the game in case you're interested. I've primarily been working with Enrico, but I've also been working with some other grad students of his and some other grads. Morgan, in particular, is working on red giant disruptions. And I forgot to put him up here, but Sheng Fei, a student at Big Games, also working closely with me on this stuff. Okay, so during a tidal disruption, you basically take the initial thing that's coming in and you transform parameters, whether those parameters are of its orbit or of the properties of the object itself in terms of how bound it is to itself, and what the properties of any mass that are removed from that object are, is set at the time the star or anything that can be experienced tides approaches pericenter. So in outline of today's talks, I'm going to give sort of a brief overview of the analytical methods people have used to study tidal disruptions in the past. I'm then going to show you some hydrodynamical simulations that I have performed, and also show you some results from earlier work by others. Then I'm going to discuss 4 discoveries that either myself or others working on this problem have made on tidal disruptions through these simulations. And lastly, I'm just going to give you sort of a practical application of these discoveries. So how can we use our new knowledge in a meaningful way? Okay, so one of the first things that one can consider is if we have no mass loss, and I just raise a tide on the surface of a fluid object, it takes energy to lift that mass out of the object's potential well. The energy has to come from somewhere, and it ends up coming from the orbit of the object. And when you do this, you excite these normal modes of oscillation, which are typically decomposed into these spherical harmonics. And primarily, you're exciting a L2 oscillation. So the way that it's tackled in the case where there is no mass loss before, it's just sort of in the grazing limit where you can approximate the object as being spherical, but on top of that, you add a small perturbation, which is a linear combination of these normal modes of oscillation. So at larger and larger distances from the perturber, modes of longer and longer periods are excited. And it turns out that as you go to higher L/M, the periods of these oscillations get longer. And so when you have something that passes by a perturber, not too close of a distance, you tend to excite a number of these modes. So this was tackled by Preston Tucholsky in 1977 and others, where you're just doing a convolution of the time change of potential with the response of the object. And from that, you can determine what the amplitude of all these modes are. And that gives you a measurement of how much energy you're dumping into those modes. The advantage of this method is it's cheap, it's simple to calculate, it works at large distances. Unfortunately, when you start getting close, the concept that the object is remaining spherical starts to become incorrect as the star itself starts to deform, sort of at order unity. And in that case, this model breaks down. You can't use it. So another approach has been to just simply treat the object as this deformable ellipsoid. And this ellipsoid is essentially resolving the primary mode that's exciting this encounter, this L2 mode. And that allows you to actually look at sort of more dynamical response, or the aspect ratio of the object is changing dramatically. Unfortunately, if you do this, you lose all information on these higher order modes, which are important for grazing encounters. So both of these methods treat the case where you have no mass loss in sort of different regimes. And they both work in sort of limited ranges of parameters. Now, if you start to care about mass loss, the Mikulski method doesn't really get you anywhere because you're presuming it's never deformed. So the two ways that people look at this typically is sort of a Roche surface treatment, which is what we were talking about at our fluids meeting a couple hours ago. In this case, you can sort of treat a slowly evolving system where mass is slowly draining out of one point. But it's not good for, say, looking at a case where all the mass, or half the mass, can be removed in a dynamical time scale. The other way is, another approach is to actually take the model we saw on the previous slide where you treat things as a deformable ellipsoid and essentially nest them to generate a nested ellipsoid model of the object. And this actually allows you to measure the mass loss by just making the assumption that when the aspect ratio of these ellipsoids exceeds a certain limit, you consider that mass the velocity of the object. So, unfortunately, this method makes a lot of simplifications as to the complicated physics that are going on in these disruptions. And so it's not clear, although I'll show later that actually does a fairly good job. It's not clear if this can actually treat tidal disruptions well. Okay, so if we now try and use numerics to understand this better, there are two primary approaches. The first approach, which I think has been used much more widely, is smooth particle hydrodynamics. Here you're treating the problem in the Lagrangian sense. You discretize the star into a bunch of equal mass particles. And then you just throw those particles by a mass perturber and you look at the results. So over the years, this method has increased the number of particles that are typically used. You notice here this model here by Delphinius and Katz has a whopping 50 particles. Amazingly, this reproduces the change in energy within a few tenths of percent, which is pretty amazing considering the smoothing length is on order, or involves on order of 50 particles. So the key is that to get the bulk mode excitation right, it actually doesn't require terribly much resolution. It goes to the limit where things are getting deformed by order of unity. The other approach is to do it in a grid-based way. Now, the challenge here is that we're no longer doing things in the Lagrangian system. We instead have a fixed grid in which the fluid is moving through. This can cause problems with tidal disruptions because the speed at which the object goes in pericenter can be many tens of times larger than the internal sound speed of that object. So it becomes tricky to properly treat balance of the object's own gravity in a system where it's vectoring across the grid at high velocity.
Isn't it back off the bud speed that the known guys?
I'm sorry, could you repeat the question?
Isn't it just back off the bud motion, the center of mass motion?
Yes.
Because you only have
And that's exactly what you did. So you put things in the frame of the object being constructed, and then your speeds are reduced to approximately Mach 1. And things perform a lot better. You can actually do the balance much more carefully. So we can actually use this. So this has been mostly done by a group of Russians in the 90s. And then I did it with Enrico's group more recently. And so you can use this to actually look at the regime where the tides are weak. And the reason, the advantage we have over the SPH calculations is that we have a much improved spatial resolution. And we can actually resolve very low amplitude modes and modes of high order in this code robustly. So what I'm showing here is an animation showing a grazing encounter where the perturber is basically swinging around in an arc like this. You notice that there is some artifacting here, this sort of moire pattern of grid cells. This is our Cartesian grid that you can see imprinted on this. But I'm just showing the perturbation. And in this case, the change in energy is something like 1/10,000th of binding energy. It's a very small fraction of energy that's in this oscillation. So there actually
Any change in shape?
there is a slight change in the shape in this case, but
The perturber is running away. It's hard to see that.
yeah. So I've outlined the star's radius in red, so you can see what it is. So I'm just showing you here the differential in pressure. It's hard to see the edge of this object, but it's approximately where that red circle is. Anyhow, so you excite all these modes of oscillation that I was talking about, even the high order ones, and then we compare this to a code by his name on Christensen Dalsgaard that calculates these normal modes of oscillation for main sequence stars, and we found very good agreement in terms of the frequency of these oscillations and in their amplitude. The main problem that we've identified so far with this method is that the L4 mode, which is the green one here, you have a bit elevated excitation. And we think that's because of this Cartesian grid, which you're seeing on the right here. It has a 8-fold symmetry, and so it tends to get preferentially excited.
What code is this?
This is Flash that I'm using. Okay, so if you now do sort of a systematic study and you just ask what's the change in energy when I vary the distance at which the object comes to the perturber, you find that the change in energy seems to agree pretty well with the analytical prediction, which is this dashed line, in the case that it's fairly grazing. You have a little bit extra energy change than you did from the linear model. And this is likely because you do actually have a slight change in the size of the object for the grazing encounters that is not assumed in the analytical model. However, you notice that you start getting deeper and deeper, so here's the pericenter distance on the bottom, this change in energy starts to go the opposite way. In fact, it goes negative. And what's happening here is that mass is being lost from the object at pericenter. So this is a little bit surprising. Yeah.
What's your definition of tidal radius here? Is it different than the rotor radius?
So the definition I have is just a mass ratio of 1/3 times the star's radius. But it's sort of, it's just to put a number here. I'm not using it to say define it.
What's happening about the axis?
So here, get thinner and thinner lines of higher and higher resolution numerical simulation. So what I'm showing is that at a certain point, the amplitude of the tide is smaller than the grid cell. So the simulations don't resolve the tide properly. So the only way to combat that is to increase the spatial resolution. And what I was just showing here is that we have convergence out to about 3 times the tidal radius, but beyond that the tide is more small.
This is nice.
This is a grid base.
And can you do better with SPH?
No, you do worse with SPH. The problem is that you have equal mass particles in SPH, and because of that, most of your particles tend to be concentrated in the dense core of the object.
There are methods to do unequal mass particles.
There are unequal mass particle methods, but they suffer from numerical noise problems in that if you have light particles and heavy particles coexisting, you tend to get a lot of noise in the lower mass particles from bouncing off the higher mass particles. So some people have done these sorts of things, and in principle there might be a way of doing it correctly, but there are big noise problems. Okay, so the surprise is that you get this positive change in energy, which is a little strange, right? Because the energy has to come from somewhere. So where is it coming from? I'm showing here 2 cases. This is a paper I wrote on the disruption of giant planets. This is a paper I'm writing with an undergrad in Enrico's Guillochon, where we're doing this with main sequence stars. And the kick that you're getting is sort of on the order of the escape velocity from the object itself. So not hypervelocity stars, which are 1,000 kilometers a second, but pretty substantial. So what's happening here? It's a little bit hard to see, but there's essentially asymmetric mass loss. Okay, hopefully, a little bit. So the point is that the tide on the near side of the object is slightly stronger than it is on the far side of the object. And because of this, you lose slightly more mass through L1 than you lose through L2. So where is the energy coming from? The energy is coming from the binding of this mass to the perturbator. And at the time it is removed from the object, you have an exchange of energy where the mass that's being removed sort of has one dynamical time scale to exert one essentially stellar acceleration on the surviving object. So what this means is that you end up with a situation where the change in energy goes as the pericenter velocity times the escape velocity of the star. Because you're removing this mass at pericenter, and you're interested in the differential as the parabolic orbit has 0 energy. And so that's what you get out. So you get a very nice linear relationship between the difference in mass between L1 and L2 and the change in orbital energy. The thing that complicates this for more grazing encounters is that you're tucking some of that energy away into the normal modes, which are always negative when the star comes in irrotational. Okay, so this is a discovery not originally made by me. This was made by Joshua Faber in 2004, where he talked about giant planets. But I have verified it in my code, and Sheng Fei has written a paper recently where he includes the cores of these giant planets to see how that affects things. What's interesting is that if you look at this linear relationship, no matter what the mass of this core is, they lie in the same relationship. So all that really matters is the differential of mass being lost by 1 over.
Just a quick question. The normalization here is quite large. The change in the orbital energy, both in the orbital energy,
Right.
the orbital energy.
So
And yet the binding energy for the disrupted object is made it small compared to the orbital.
So in a planet, for both supermassive black holes and black center and for a planet, they tend to come in on these near parabolic orbits. For giant planets, they're scattered into the ice bodies. So their energy is small. The orbital energy is initially small.
The velocity that you showed before, 400 kilometers per second, those are refer to supermassive black holes.
Yes, supermassive black holes.
So how do those velocities depend on the structure of the star? You have to have a diamond.
So I should have specified this. These 2 curves here are for 2 different polytropic gametes.
Okay.
So these are sort of sun-like stars, and these are low mass stars. The 4/3 is more centrally concentrated than 5/3. So it doesn't, I mean, it matters in terms of what kick you get at what distance. Sorry, beta here is the impact parameter. But the fact that it truncates, so up here, these are the most disruptive encounters. Beyond a certain depth, the stars are just destroyed instead of producing a surviving node at all. So, of course, there isn't really a kick. It's just a stream. Okay, so I was interested in what happens when we vary these two parameters. The impact parameter, which is how close you get to the perturbing object, and gamma, which is the polytropic gamma. So I did a parameter study where I varied both of these terms. And this is for the case of a main sequence star being disrupted by a supermassive black hole. And so I'm just showing you here a snapshot at the same time from all these simulations. So the stuff that ends up getting bound to the black hole is this near tail debris, the stuff that gets tossed back onto the black hole after the disruption. And so the question one might ask is, what's the rate that that material falls back onto the black hole? And so what I was wondering was, how does that depend on how that mass is thrown out from the star at pericenter? So calculating the rate of fallback is relatively straightforward. You just use the chain rule to find the rate of fallback. You have a spread of energy across the mass at pericenter. You multiply that by the EDT, which comes from Kepler's law. This dMdE could potentially depend on many things: the mass of the black hole, mass of the star, radius of the star, gamma, and beta. Typically, the typical assumptions we made is that this is flat. And this is an okay assumption if you're considering the bulk of the material, because the centers of polytropes are flat. So the spread of energy across the center of those polytropes is flat. And if you do that, then this term here gives you a t to the minus 5/3 characteristic decay. So now let's ask the question, what happens when we vary all these parameters? So it turns out, if you vary the black hole mass, not much happens. The reason is that the time of the crossing is constant at constant impact parameter. And the impact parameter has been scaled to the tidal radius. So that means that the force applied as a function of time is the same in both cases. A difference is, though, is that the spread of energy across the object changes as you vary the black hole mass. But this only leads to a systematic change in the resultant fallback rate. The thing that could screw this up is, say, asymmetry in time. So it turns out for a supermassive black hole, the mass ratio is so large that the difference in the strength of the tides on both sides of the object is small, the order of a percent. So you can vary all these other parameters as well. All of them, so black hole mass, and stellar radius can all be marginalized over the definition of the tidal radius, which depends on those quantities. And they all lead to basically systematic changes of the fallback rate, but no changes in shape. That's the important thing to remember. So for the majority of stars, you can write out the mass accretion rate as a function that looks like this, that depends on these three parameters in this way, and a function that depends on beta and gamma. So the question is what are beta, so how does this depend on beta and gamma? So as I described, beta is the ratio of the tidal radius to the pericenter distance, and gamma is this polytropic index. And for stars, the polytropic index ranges between 5/3 and 4/3.
I'm confused. The gamma also, you all have an equation related to gas, which you don't call gamma, I guess.
Yes, so there's the equation of state of gas, it turns out, is always gamma equals 5/3. The structure, though, the polytropic structure, is different because of the radiative transfer that's occurring within the star. That alters the steady state structure of stars that primarily transport energy through radiation transport.
So your adiabatic gamma always has a
always
when you say gamma, you really mean the phototropic end.
That's right. So this is setting the mass distribution within the object, but it does not actually specify the adiabatic response. Okay. So a second discovery we have in these simulations is the amount of mass loss as a function of beta and gamma. So what I'm showing here is a delta M on the y-axis and the impact parameter, the x-axis, and these two curves are from those runs of simulations I showed before. The tricky bit is the critical distance at which a remnant core will form or not. So here I'm showing two cases, beta equals 1.8 and 1.9. So they're straddling that boundary where a remnant core forms.
Smaller beta means go closer to the black hole or further?
Further.
Further, okay.
So in this case, you have a recollapse because the tidal gravity was not strong enough to hold this stream such that it would not essentially suffer Jeans collapse. And so this exact boundary is difficult to calculate analytically because this is where things get very nonlinear. As you notice, the recollapse happens within the stream long after it seems like the core has been disrupted. So this is a tricky boundary to calculate any other way.
What remnant masses can you have to evolve?
Hundreds of solar mass. It becomes progressively more tricky the smaller it gets, but fortunately that's an ever-shrinking region of parameter space if you're interested in such low mass things. Okay, so the third discovery we made was the shapes of these fallback curves as functions of the structure and the impact parameter. So remember before I had said that the fallback is typically assumed because T to the minus 5/3 because we assume that the energy distribution of mass is flat. So a interesting thing that we discovered is that this is not entirely true. In fact, you can see that these lines sort of dip a little bit more steeply than the standard T to the minus 5/3. Why is this happening? Well, the simple model that people have been using in the past is that, okay, if we want to figure out the spread in energy across the object, let's just take the spread in energy at pericenter and use that to construct a PM ED. And then convolve that to, say, the mass profile or the polytropic profile and get a function of PM ED. Unfortunately, it's incorrect in the sense that at pericenter, the material is already all flowing on free trajectories. If the star has gone deeper than the tidal radius. So really, the time at which you should freeze the energy distribution is closer to where the tidal radius is, where the object is actually destroyed. If you do this, you find that the spread of energy doesn't really change very much at all as you change beta beyond the tidal radius. So if we go back to this, what you notice here is that all of these pink-colored lines, which is deeper encounters, lie pretty much on top of each other. If you just say take the energy spread at pericenter, you expect the peak of the fallback rate to scale in this way. So you'd expect for a very deep encounter with that simple assumption that you can get extremely fast flares, things that are peaking on the order of hours. But in reality, if you go deeper than beta of 1, you're not really getting any faster fallback. For the case where you have a partial disruption in the core survives, the situation is complicated, and that's just because you have this core that's tugging on these streams of material. And what determines sort of the asymptotic tail of this fallback is the stuff that's the furthest away from the black hole that is not bound to the surviving core. And the question of what's bound to the surviving core is complicated by the fluid forces that are occurring along the direction of the stream. Essentially, you're always interested in what is the last bit of mass that will fall back onto the object. And that's difficult to determine by just taking a snapshot of time. And I found that to you do all these simulations for a long time, it takes a while to sort of build up this asymptotic fallback rate.
So, in practice, what range of approximate distances on the initial type of job are you able to cover?
So in practice, my box size is 40 AU. So that's about as far as I can resolve it before.
1 AU being
1 AU is about the tidal radius. And it's very challenging because this stream is extremely thin. So you have something with a ridiculously large box to resolve a very small fraction of the box. So it just becomes more and more numerically challenging. Okay, so what's going on in terms of explaining that steepening of dMdt? Well, so in the freezing model, you basically just freeze the energy at one particular point, at one particular distance in the black hole. But really what's happening is that the outer parts of the object are getting removed first, and the inner parts are getting removed later. So the inner parts are denser than the outer parts. So what that does is it takes the linear relationship between energy and distance and makes it sublinear. Effectively, the core drags in some material to higher energies than it would be if it was lost off the same distance. So what that ends up doing is that changes the relationship between distance and energy in a way that material tends to kind of pile up in energy space. And that leads to a steepening of the fallback curve. And so what I've found is that for these lower beta encounters, the asymptotic fallback curve doesn't go as -5/3, it goes to something as -2, -2, around there. And because these more grazing encounters are more common, just because the target that you're trying to hit is bigger, it turns out that around half of stellar tidal disruptions would not be to the -5/3. And that's independent of any of the other complications that might occur as a result of fallback into a disk. Okay, so just to emphasize this, I'm showing you here an equal mass loss case where for the two different structures, they're different beta, but they lose equal mass. And the point is that the material here in the more centrally concentrated case gets pulled into higher energies. And that results in a dMdt that peaks at earlier times. So there's this recently observed flare from pan-stars, and it's unique in the fact that it's the first one that's been published that shows the rise, the peak, and the decay of one of these tidal disruptions. Every other event that we've had so far has shown just the decay, and we pick up things that are 2, 5, 5, 30. What's interesting about it is that it has apparently a little dip shortly after peak, before it flattens out to something that's more close to the -5/3. And if you take just a standard freezing model, which is what's overplotted here, it's really difficult to have something match both peak and later phase with a single with the freezing model. This is naturally explained by the dip you have in the core pulling of materials that flies by the black hole. Okay, so now I'm going to move on to a slightly different topic. We've calculated the rate of fallback on the black hole. Are we actually modeling the accretion disk that forms for that properly? So here I'm showing a wide shot of one of these disruptions. The twice the tidal radius is shown here. And what you'll see, and this is a lower mass ratio, just so that we can see this before we all leave the building. It takes a lot longer in the higher mass ratio case. What you can see is that you have this debris stream that stretches extremely far away from the black hole and pericenter. The pericenter is barely resolvable here. The standard assumption that's been made in the past is that this accretion disk, because it has root 2 GMR, angular momentum, that will circularize into a disk with a tidal radius of twice the tidal radius. This completely ignores the fact that these orbits are highly elliptical and that they're launched out ballistically quite large distances. So the size of this structure is tremendous compared to twice the tidal radius. And the other interesting fact is that this stream appears to be getting shock heated at pericenter. And that's not a completely obvious result. And in fact, all the SPH calculations that have done this so far don't see it. So what is going on here? So it turns out that when the material returns to pericenter, it's sort of like a very high beta tidal disruption. The fluid gets compressed vertically to a great degree, and you actually have a recoil and a upward going shock that forms there. And this actually virializes the flow at pericenter. And in SPH, it's not possible to resolve this because these particles file in one by one to pericenter, and you never get any vertical resolution of the stream. And in fact, the highest resolved SPH simulations that have done this has something like 100 particles spread out over an AU, where each particle is something like 100,000 of the solar mass. This, I mean, really, what I've drawn here is what it looks like in SPH. So you can't resolve the vertical structure. I think this is critical to understanding the resulting structure of the accretion disk. Because what it does is that it allows the material to be virialized at pericenter instantaneously. You don't have to wait for it to return back and funnel back in through a accretion disk that slowly spirals back to pericenter. If you had to do that, the time scales don't work out. You have to wait for the viscous time at the point of the collisions higher up in the stream, which is way up here, to virialize the flow. And so M dot won't follow L very well at all. If you do that, you can't make tidal disruptions work at all. It just won't work for any of the cases we've observed so far. So I think this is critical for understanding this. And I
don't see anything like accretion disk formulated. It's a stream passing by, right?
That's right. So it turns out
it doesn't relax at all to any sort of this structure.
So that is true in that it's not full annuli that you're seeing. It's these ellipses. However, it turns out that the temperature that you get at pericenter is the virial temperature, and when it expands out, it's in tidal balance with the black hole with radiation pressure. So it actually falls off at R to minus 3/4 in temperature, the same way a Shapiro-Sunyaev disk does. So here I'm showing a sideways cut through this same simulation. And sorry, I played too close. And here what you notice is that there's quite a bit of vertical spread of the debris, and that it is in rough tidal balance.
And that stuff is bound.
That stuff is all bound. So all of this is bound. What you're seeing here is actually a cross-section through the debris stream.
Is this kind of another way of saying that it takes multiple orbital times for the gas that to circulate?
Yes, yes.
But then what's going to happen?
So you mean in these simulations or under the standard model?
Well, in the standard model, it's up to 1 but so what are you actually finding?
So what I'm actually, so I think what the standard model does is it says everything comes back to RT, and then it just kind of circularizes on that orbital time scale. But that's incorrect because that material is ballistically launched out to hundreds of tidal radii. So the coincidence of being able to have M dot strongly linked with L comes from the fact that you've made the wrong assumption about how far the material goes out, and you haven't taken into account the fact that it can shock virially at pericenter when it returns. So if those two things combined, you can still have L all over the time.
So I'm asking how many orbital times does it take for?
A few. It depends on what your alpha parameter is. So and that's another challenge, is that if you have alpha significantly smaller than, say, 10, then even if it is circularizing at QRT, it won't match any of the observed light curves.
I think it's worth pointing out that those light curves
Yes.
maybe then they're not that really shocking.
That is
We don't necessarily have to say like those are.
it is a distinct possibility. And so this is the only way you're going to be able to understand the tidal disruptions themselves. Sort of calculations like these to determine at least what the bulk properties of the flow are.
Well, then what happens? have you followed things in any case? Like, so you still have this sort of elongated streamline structure, which you could pick up properties under the very elliptical disk. But it doesn't close. But you have this sort of hoop-like structure that is apparent at the end of the simulation.
So it sort of closes in a way. Sorry, I'm showing you these 3D snapshots now of that same thing. I'm sweeping through isodensity contours just so you can see the different.
And this very low density stuff that does.
It's low density stuff. It also has a very large opening angle in the vertical direction. So you can see, you can see actually if you look carefully here, that material, the dense material, is getting chunky to some degree by.
So the previous movie was showing us the higher density stuff.
Yes.
I was missing this.
Yes.
So to speak.
Yes. So this is also a problem.
But then the stuff that does close is closing well outside 2 RT.
Yes, that's right.
It's like 10 RT or
100, very, very far out there.
so very long time scale with that.
Yeah, and it definitely depends on the amount of spread that you have at pericenter. And so in this full 3D simulation, even though we have some vertical resolution of the nozzle point, it's not good enough really to say in detail what's happening at that point. It's hard to get the exact degree of compression that you're getting.
But there's still this dense hoop of material, or that hasn't yet clearly relaxed, right?
Yes.
It's closer in.
Yes.
And so it sounds like it would bear continued evolution numerically to see what that does.
Yeah. So I've run this 10 to the 3 encounter for quite a while. And there, the nice thing is that the return time is short enough that you can resolve it going up the peak and into the tail to see how things change. Qualitatively, it's the same behavior at all times. But that being said, we don't have all of the physics input into the nozzle or into the equation of state at this large scale situation.
Well, actually, when you're giving those nice plots of m dot versus time, how do you actually define it?
So m dot is the rate of return to pericenter the first time.
The amount of mass passing through a sphere, the radius RP.
Yes. Okay.
Is there any artificial viscosity?
There is numerical viscosity, which is relatively small for the hydrosolvent that I'm using, but there is some. The majority of the viscosity is coming from the shocks. Or rather, the majority of the change in entropy is coming from the shocks, which are, effectively a form of viscosity.
So you're pretty confident that that doesn't affect?
I'm pretty confident. So the simulations I showed here are very high resolution 2D versions of that nozzle point that I performed. And you very confidently see this shock structure in those high resolution simulations. I haven't done, so this is not time dependent or anything. This was just to see what the steady state shock structure looks like and if it's consistent with the previous simulations that we've done. Okay, so that's this. Okay, so now maybe that we have some preliminary understanding of what's going on in these with the fallback and with the resulting accretion structure. You might ask, can we gain any knowledge or maybe doing a systematic study to the events that have been observed? Can we maybe eliminate some as potential tidal disruption candidates? So I developed this software. It's a markup chain Monte Carlo code that just does fitting. It takes my simulation data and it basically forms a teardrop shaped accretion disk that forms from that we expect to form from the fallback. And it just produces light curves. And so, you can vary many parameters in this problem, but it turns out that many of them aren't important. Anyhow, so I've done this exercise for this CanSTARS event. And so what I'm showing you here is 2 fits where we've used the standard Shakura Sugaya model of secretion disk. In the first case, I've truncated it at twice the cutout radius, which is the standard assumption. In that case, this is the best fitting model. It's very, very difficult to get enough luminosity to explain the inherent magnitude. So now I said, okay, let's presume that gets shock heated and it gets launched out to large distances. So now I let that same precursor I just extend out to a much larger distance. They get a better match, but it's not great. You can see that the
Well, but why if this extends to a larger distance, do you get a faster rise?
so it has to do with the particular combination of parameters that fit this.
So if you want to fit the tail, then with that geometry, you get more of a...
That's right. So you, in this case, the code, you know, it's minimizing chi-squared.
But how much luminosity do you get just from the internal dissipation and measure in your simulation, dissipation due to the presence of shocks and so on?
I mean, it's the structure that results is very similar to precursor ions. So the luminosity that you get out is basically the same. With the added complication that you're not covering the full annulus out to the outer region, so you have these ellipses. And so that reduces the fractional contribution of the outer parts of the disk relative to if I had a full annulus.
Maybe I'm asking this question completely different. If you shock this and heat it a lot, it doesn't radiate, but it's still way too optically thick.
Oh, it's way too optically thick to radiate instantaneously.
So it does need time to sort of,
Yes.
less time to sort of circularize that.
Yes. Okay, so I did this.
Where does it radiate? And I actually still am confused.
Well, so it's radiating at a photosphere at the surface of the fluid, just like a standard precursor.
Exactly, that must be mostly on about a large distance.
It can be, and that's a problem. So if you go back to this, the density contour of the tau-1 surface, so this particular simulation, I don't like to take the numbers literally because I'm not using the exact right equation of state or the right mass ratio. But if you scale this up loosely to 1 to million, the tau-1 surface is sort of one of these intermediate contours.
I see. Okay. Actually, we really shouldn't completely be thinking as a disk at all, but some kind of weird shape.
Yeah, something like this. What exactly that weird shape looks like is going to depend on more detailed physics and cooling.
And is then most of the heat, is that in fact from that shock?
Yes. So most of the energy you're getting is from that shock. Now, of course, the complication is that you want to get most of the energy in the AGN disk from the ischemate. That's where most of it comes out. But it comes out in X-rays. And you're not observing X-rays in these systems, you're observing optical energy. So you're kind of wagging the dog in that you have a part in 100 of the light or something like that. And you're trying to actually figure out where the properties of the volumetric light curve from that small fraction.
In that one event, what's the luminosity effect of the estimated editing luminosity?
It's just below at infinity.
Are you inferring a black hole mass from your model too?
Yes. So what I found. So here's the complication. It seems like that even with all this modeling that I've done, we don't have the answer. So this is showing you just a simple blackbody fit, presuming the disk can extend all the way out to that distance. And it doesn't produce that great of a fit. What produces the greatest fit, and this is pretty stupid, is a simple blackbody of a fixed temperature whose luminosity just changes linearly with m dot. It turns out that this gives you a pretty darn good fit. And the fact that this red here evolves a little bit at late times relative to all the colors sort of forces the fitting software to simultaneously match the peak and the tail with a less than optimal solution. But if you actually just take the first half of the data and you fit that, you can get an extremely good fit, that part of the data, just by following m dot. The problem is that how the heck do you produce a simple blackbody, a single blackbody curve from this very complicated looking flow? The reason why it's necessary.
Because I'm still confused. You just said that it's so hot that it really should emit mostly in the X-ray. So that means you're really getting this sort of regime still, or is that?
Yes, this is so you can see that here.
Okay, sorry, yes.
These are each of the bands right here, and this is the peak lead.
Do you also that it's really optically thick, right? So even though it's hot X-rays down to the disco,
Yes.
you've got all this stuff on the outside.
Yes.
So reprocessing on the inside.
That would be the host. The problem is that, so here's a potential model for doing it, that you can sort of float these clumps of material that reprocess the outgoing radiation to produce something like a big blue drop, which is observed in the GM. The issue with it is that the total covering fraction of these blobs cannot be terribly greater than 1. They have to be on the order of 1. Because if they're greater than 1, the blobs intercept the radiation, and then they adiabatically expand out a bit and then cool. And then you just have a lot of adiabatic degradation of the light itself. And that makes it difficult to actually produce it with the tidal disruption. So really you need some mechanism that is able to provide you with close to 100% coverage, but not much greater than 100% coverage, such that it can reprocess all of the outgoing light and essentially put most of it into a single temperature blackbody that's actually looking to. Now this part of it, I haven't done direct work on that particular part of the modeling, but it's definitely a puzzle as to exactly how one does that. So I've done the same exercise now, and I just said, okay, let's presume that the simple blackbody is what comes out of all of these events. Because that seems to fit the best observed one.
So I'm still slightly confused, I guess. So you have L scaling as M dot issue, which you have, and then you basically say it's a single temperature, so that sets my area.
That's right. So you can think of it this way, where it's a sphere whose size changes proportional to R v. Sorry, L minus 1.
Basically, somehow this equation, your M dot is really good, I guess. That's really good.
That's right. That's right.
And somehow it has to convert that to luminosity in a way that keeps temperature roughly constant.
That's right. So the problem is like if you do a Shapiro-Sunai disk, to show this here with this older sort of one, you have too much color evolution. So you can see here clearly the distance between, so red is sort of early times and blue is late time. You see the difference between the blue and the green in this band is much larger than the difference in that band. And that would produce a very wild, very wildly different UV band than optical band. So you have to avoid that, and that's the challenge of making a good model for this.
Well, again, there's this subtlety here. When it's conditioned a bit by thinking about accretion disks, where I have a certain mass transfer rate. I could actively go up there. At some point, I reach, say, there's a high mass transfer rate. I reach a local dissipation rate equal to the energy velocity, but then further out of the disk, it's still it goes like R to minus 1.
Right.
But here, you're drawing, it's incredibly superactive. Right? Everywhere it's superactive.
No, it's southern.
No, the dissipation is going to be super.
No, so it's southern. The fallback rate is below the energy limit in this case. I guess I'm confused about it.
Okay. Well then, okay.
So you do this exercise for all the other observed events for which you only have the tails. And you just use the smart chain Monte Carlo to constrain the distributions to the parameters that are possible. You can start to measure things like the distribution of impact parameters, the distribution of black hole masses, and the distribution of stellar masses. Now, of course, I only have 6 events, so you shouldn't take these literally at all. However, once you start accumulating a few dozens of these events, you can start playing these exercises. The key thing is that we have to identify where is the emission coming from. We have to actually get a model for doing that, because the particular best fitting combinations depend on how mass is converted to light. So really, we want to, we want to have a physical explanation as to what's going on for this to actually have any meaning. But I think that one of the ways you can do this is you can compose a model, measure these distributions, and ask, are those reasonable distributions? For the simple blackbody case, the distributions are reasonable. We have basically cutoffs at low parameters, at these low parameters, because they're less luminous. So we have a sample that's selected based on how bright it gets. You're going to miss the dimmest event. And then the distributions and the higher ends are what one expects for the distribution of impact parameters, black hole mass, and stellar mass, roughly. But we can always ask the question, okay, does the particular distribution that comes out of this exercise actually make sense? hopefully can put some limits on the model. Yeah, and so the future power will come from when this number of observed events that are well sampled have the rise, peak, and tail much greater than 1, which it currently is. And hopefully pan-star's collaboration will start releasing a lot more of these. And I think what prevents them from doing it is that their fallbacks for many of these events are not Q minus 5/3. So they're like, okay, that's not the Tidal stuff. But I think what we showed is that the m dot, even just linking m dot to L, it's not Q minus 5/3. So they should be a little bit, maybe more liberal in their cuts. Okay, so linear theory only takes us so far. We've made some new discoveries through numerical simulation, which can at least be qualitatively understood through some analytical arguments. Now that we've done this exercise, I think our biggest challenge is to just understand where does the outgoing emission come from? How is it actually produced? Thank you.
So what is the temperature that you find? What does it vary between the sources? So let's take this blackbody model series.
They're pretty cold. So they're on the order of a few 10 to the 4 Kelvin for the temperatures. And of course, the ISCO temperature is much higher than 6, 10 to 7 Kelvin. That being said, you do expect the light, even though the occurs in IFS, to be dominated by parts that are colder, but not that cold.
Yeah, when you are modeling those events, through the luminosity, you assume it's related to the fallback rate.
Yeah.
So are you worried that the accretion rate after the black hole may not be exactly follow the fallback rate?
Well, so what the large scale simulations seem to indicate is that you shock the material at pericenter, and that's where most of the energy injection is occurring. The time scale there is relatively short compared to the time scales in which we're observing these events. So that the orbital period at pericenter is about a day. So the hope is that if you can convert the energy relatively quickly from m dot to L close to pericenter, then you have a fairly strong relationship between m dot and L.
So you're thinking that the radiation also comes from the region at the pericenter?
Yeah, so there's some fraction that comes from there, but I mean, you think the same accretion disk processes that happen with AGN happen here too. They just happen after this initial sort of preparation of the fluid at pericenter where it passes through this oscillator.
Okay, you have a size, right? From your nominal sphere, is that sort of 10 AU or 1 AU?
It's on the order of 10 AU. So it's on the order of sort of this blood bubble scene.
So that is about 10 AU.
Yeah.
You guys have this bubble, but then as the last dregs, it's very come back in, they would tend to interact with the larger rate because they somewhat stuck when they encounter this pre-existing.
Yeah, you tend to build up this bubble that takes a while to go away, just because you have to wait for that stuff to be back on the black hole.
So eventually, there has this sort of barrier to the tail, the last tail getting in.
Eventually, but in very late times. The tail is
Very compact.
Very compact. So that allows it to sort of plow through this.
Last question. So you have been just treating the luminosity from this way, having gases getting going out there and pressure.
Yeah, I haven't included any of that because I mean, in truth, something like that could be the way out. But there's a lot of freedom in the models, for me at least, to put them in. And so I just haven't been, there's a number of papers I've looked at, the dMidr being one of them. I just haven't been particularly enamored with any of I guess the explanation. So heavy load has one too. It's much simpler than noise. It's just like when you build this radiation pressure supported bubble. But that isn't working anymore. to answer your question, I think nothing I've seen explains it really well. I think you need to think a little bit more about what's going on. It's something similar to the big blue bump, whatever produces that. Probably what's going on, but big blue bump tends to be the 1/10 of the light that comes out of the equation. Where here we have more like all of that. So, okay.
Okay, so let's continue the discussion upstairs over cookies, and I'll send an email out